Previously, I used an example of the recorded backup beep from, say, a UPS truck, and talked about how each beep sounds the same, but there's different noise each time we listen to it. And so here I've written the equation for something like that. Here we have y would be our observation is equal to the cosine of omega n, that would represent the beep, plus some random variable x, and that would represent the noise. Well, because there's noise or a random variable anywhere in this, both x and y are random processes. And so we can take the expectation. The expectation of y of n is equal to the expectation of x of n, because expectation is linear, plus cosine, because the cosine is not a random variable, and so the expectation just disappears. So that's just equal to the mean of x of n plus cosine omega times n. So if the mean of x is 0, then the mean of y would just be cosine of n. In other words, the mean is a function of n. Because the mean is changing all the time, this is not a stationary process. This is a new term that we're introducing now. Because my of n is a function of n, of course that's implied down below, so y of n is not a stationary process. So let's define stationary processes. A stationary random process is one in which the probability density function does not change as a function of time. Now for us, we're doing discrete time signal processing, so I'm just going to put it does not change as a function of n. First off, this implies that the mean and variance are both constants. And so we can say that mx is equal to the expected value of x of n for all n, and we can drop the subscript there too. The variance is equal to the expected value of xn minus mx times xn minus mx conjugate, also for all n. Furthermore, the autocorrelation is only a function of the difference in time.